An application of finding the extrema of a function is that we can use these to solve optimization problems. So how much do you think about real life instances where you want to know things like the greatest amount of profit, the least amount of cost, the least amount of time? So these are all sorts of things that we would do. So here's an example, and this is a really common one. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches, as shown in the figure below. What dimensions will produce a box with the maximum volume? Now, why may you want to do that? You may have like one sheet of cardboard, so you have a finite amount of surface area, but you want to make sure that you create a box that has the most possible volume to fix the most possible things. So the main idea that I want you to take away, we always get kind of stressed out about these problems, but these are just maximum and minimum problems. That is it. Optimize simply means to find the least possible of something or the most possible of something. We can say maximize or minimize, but optimize covers all of those things. So these are just max and min problems. So let's look at a couple that we'll go ahead and work out. On the next page, you see a little bit of a summary of the process that you want to follow. So similar to when you look at related rates problems, make sure that you figure out what are all the things you've been given and what are all the things that we need to find. If it's something that's geometric or visual or graphical, it's always helpful to have a sketch if they don't give you one. You're going to write two equations. You need a primary equation that's going to describe whatever thing it is you want to be maximized or minimized, okay? Then you're going to need to use a secondary equation, maybe to do some substitutions so that you only have a single variable in your primary equation. It's kind of like working with systems in that case. Figure out what the domain of the primary equation is. Essentially, we're just saying, what are the values that make sense here? Like negative values for area wouldn't make sense, so we wouldn't include that in our domain. And then using what we know about finding extrema, we're going to determine the solutions there. So we're going to look at just a couple of examples. I'm going to leave the rest for you to look up on the notes that are posted online. So I want to start with this first one here. This is more of a abstract graphical approach. It says which points on the graph of y equals 4 minus x squared are closest to the point 0, 2. Now they say which points because we know about the symmetry of a parabola. If this point 0, 2 is in the on the axis of symmetry there, these two distances are going to be exactly the same. So there's going to be another point over here that's going to be negative xy that is also going to have the same distance from the point 0, 2. So the question is, our primary equation, what are we trying to maximize or minimize? We want to get closest to the point, which means we want to minimize the distance. So our primary equation in this case will be the distance. And for that, we can use the distance formula. If I want the distance from any point xy to the point 0, 2, distance is equal to the square root of x minus 0 squared plus y minus 2 squared. Okay? And so we can make a substitution. They've already given us a secondary equation. What this allows us to do is we can take out y and replace it with 4 minus x squared. Then our distance formula is going to become a function of x because that'll be the only variable that we have. So we have the square root of x squared because that's what x minus 0 squared will go to. Then we need plus, we're going to take out the y and replace it with 4 minus x squared minus 2 squared. That's now our function all in terms of x. Now we can do a little bit of simplifying here. So we get the square root of x squared plus 2 minus x squared, squared. And so that comes out to, when we square everything out, we get x squared plus 4 minus 4x squared plus x to the 4th. And that leaves us some like terms. So when all is said and done here, we have the square root of x to the 4th minus 3x squared plus 4. This is the function that we want to minimize, because we want to be the closest. But this is the function where we need to look at the derivative and all of that. Now, here's a little trick that we can use. If I want to maximize the value, I keep saying maximize. If I want to minimize the value of that radical, all we need to do is minimize the value of the radicand. The smaller the number under the square root is, the smaller the value of the square root is going to be. Square root of 2 is going to be less than the square root of 5. So we don't even need to take the radical into account, which makes our derivative much, much easier. So I want to look at d prime of x, which is going to be 4x cubed minus 6x, which we then need to set equal to 0 to find our critical numbers. So we can factor out a 2x here, and that gives us 2x squared minus 3. So our critical numbers are going to be x equals 0 and plus or minus the square root of 3/2. Okay, those are our two values here. Now, do we need to place any restrictions on the domain? No, because that graph, the domain of that parabola is going to be negative infinity to positive infinity. The distance could be 0, or it could be anything greater than that. Distance is the range. The domain, we can plug any number in for x, and it's going to give us a distance using that distance formula. So we do not need to restrict that at all. So now we're going to come down and look at our values. This is the values of d prime. So we have negative square root of 3/2, 0, positive square root of 3/2. Now, I still don't know what the square root of 3/2 is, but I know that it's barely bigger than 1, and I know that it's definitely less than 2, because 3/2 doesn't get us to 4. 3/2 is less than 4, so I know that the square root of 3/2 is going to be between 1 and 2. I don't know what, but it's definitely going to be somewhere there. So when I pick values, I'm going to pick a value that's less than 1, and I'm going to pick a value that's greater than 2 when I test in my interval. So if I think of like -3 to plug in here, if we think about plugging in -3, we're going to have a negative on this side, a positive on this side. So this is going to come out to be negative. And similarly, when we test, we get positive, negative, positive. We are looking for minimum values. So that means that we are looking for a switch from negative to positive, and that happens at -3/2 and +3/2. So they asked us to find the points, so we need both coordinates. So the closest points are going to be negative square root of 3/2. When you plug that into y equals 4 minus x squared, you get 5/2. And we know that the y value is the same on both sides, so the other one is positive square root of 3/2, 5/2. Those are the two closest points. There is nothing different about this than any of the other maximum and minimum problems that we have done, okay? I'm going to leave the next example as one for you to look at on your own, and I would like to look at the top example on the next page. So it says, 2 posts, one 12 feet high and the other 28 feet high, stand 30 feet apart. They are to be steadied, grounded, by 2 wires attached to a single stake running from the ground level to the top of each post. Where should the stake be placed to use the least amount of wire? So this is definitely one where we want to figure out some sort of a sketch. Here's how this scenario works. We have two posts that are 30 feet apart, okay? So I have one post, maybe right here, and another post. They're not the same height, maybe over here. We know that the total distance between them is 30. The shorter post is 12 feet high, and the taller post is 28 feet high. And there's going to be a single stake that we're going to place probably somewhere in the middle and attach a wire to the top of each post that's going to steady those two posts. All right. So if I know that one of these is maybe X feet away from the post, then does it make sense that the other one has to be 30 minus X feet away from the post? So the question is, where should the stake be placed? So we're trying to determine the value of X here, okay? So we need to come up with an equation. What are we trying to maximize or minimize? The question says we want to use the least amount of wire. So what we want to minimize is the total of these two hypotenuses here, because that's going to be the amount of wire that we use. So if we use the distance formula, when we set this up, we're going to get, or I'm sorry, not the distance formula, well, it's the same thing, but using the Pythagorean theorem, each of these distances is going to be the square root of a squared plus b squared. So for this side of the wire, we're going to get the square root of 12 squared plus 30 minus x squared. And for this side, we're going to get the square root of x squared plus 28 squared. Okay? Those are already all in terms of the same variable, so we don't need to write a secondary equation because its purpose has already been taken care of. So the function for the amount of wire, let's call it w of x, is going to be the sum of those two sides. So it's going to be the square root of 12 squared plus 30 minus x squared plus the square root of x squared plus 28 squared. Now we need to take the derivative of this, which is definitely not the most friendly derivative, but it's not the worst I've ever seen either. So we're going to have to do some chain rule here to see what we've got going on. I went ahead and multiplied this stuff out to make it a little bit easier. 144 plus, this comes out to 900 minus 60x plus x squared. Just makes your derivatives a little bit easier. Plus the square root of x squared plus 784. And so if we simplify that down, we've got that. Okay, so now we need to take our derivative. Let's do that now. I got stuck. Hold on. All right, now we need to find our critical values, and I'm certain that this would be a calculator problem. So let's go ahead and put that into our graphing calculator and find the zeros of that function. If we keep the domain in mind here, the amount of wire can't be negative. So any negative x values we don't need to consider. But let's take a moment, put this on pause, put this in your calculator, and figure out what your critical numbers are. So I find only one critical number at x equals 21. So now we need to do some testing here, because we don't just need to know, is this going to be a maximum or a minimum? This is, in a way, going to be a closed interval problem, because we could technically put the wire, we could stake it at the bottom of one of the posts. So then the wire would go straight down and it would go all the way up to the other side. That is an option. So x equals 0 is a possibility. So let's go ahead and set ourselves up a table here. Whoops. There is no maximum value that we can have, so obviously we're trying to find the minimum, so anything bigger is going to be not what we want. So let's plug in 0 and let's plug in our critical number of 21. We're going to plug this into w of x, not the derivative. So let's plug those values in our calculator. So I went ahead and plugged in one number bigger just kind of to be sure. And it does look like it's increasing on the other side of 21. So if I use 0, I get 60.31. But if I use 21, I get 50. On the other side of 21, it gets bigger. So 50 is definitely going to be the minimum amount of wire. But the question was, where should the stake be placed? So if 21 is x, that means that we want to place the wire 21 feet from the 28-foot pole. That's how we can kind of describe where we would want to put it. Okay, I'm going to leave that last example for you to check in the notes as well. This is just kind of a reminder of how to approach these problems. Setting up the equations is definitely the hardest part. After that, it's just some derivative work. And I would suggest that you use a calculator on these problems on your homework because these would very likely be a calculator question if they show up on the exam.